environmental movement that seeks to defend and enhance the environment's well-being while simultaneously increasing the possibilities for prosperity for all humanity. Our mission is to build a scientifically based grassroots movement for both human and environmental progress, and to promote and defend the growth of the sciences for peaceful purposes in the service of humanity. You can find us at esna.earth. Now, ESNA is the initials of our organization: E for Eco-Modernist, S for Society, N for North, and A for America. ESNA, esna.earth. So let us begin. Many people feel that keeping fossil fuels out of the ground is a sin, but today's topic on Synfuels is about creating the new carbon neutral Synfuels. So we would like to welcome you all to our Synfuel for CO2 Forum. And by the way, I'd like to thank our sound men and everything else, Carl Pauls, for making this possible as well. And what we're dealing with is how we get down to the nuts and bolts of overcoming our fossil fuel addiction. I'd also, before we begin, like to thank the Labor Community Alliance of South Florida for sponsoring this event. And with that, I would like to introduce our moderator, Al Scott. Al Scott is an astrophysicist who has worked with NASA. He hosts a very popular Rational View podcast. And Al Scott, take it away.
Thank you very much, Gabe. I appreciate the invite to moderate this important symposium. I want to welcome you all to the Eco-Modernist Society of North America for our second forum, Synfuel from CO2. As Gabe said, I'm the host of the Rational View podcast. It's on Podbean and all major podcast apps. If you're interested, come check it out. Also, like to give you all a reminder of upcoming events for Stand Up for Nuclear around the world, and hopefully in your city as well, or a nearby city. Throughout September, I'm going to be co-organizing one here in Ottawa, Canada, and on Parliament Hill on September 25th from 2 to 4 p.m. If you're in Ottawa, come on out to Parliament Hill and show your support for nuclear energy. There's also going to be one in Seattle on September 18th. So if you want to find out more about Stand Up for Nuclear, you can go to their global website at standupfornuclear.org and check out my podcast from Saturday last, interviewing Paris Ortiz Wines, the global director of Stand Up for Nuclear. So on to why you're here. Our ability to leapfrog over our fossil fuel addiction and thus decisively address our climate crisis will literally be mission impossible without serious scientific and technological advances. One of the most important of these will be our ability to mass produce carbon neutral fuel sources. Our expert speakers today will be Dr. Surya G. Prakash and John R. Bucknell. Dr. Prakash is a world-renowned expert on hydrocarbon chemistry and associated economics. He holds the Olah Nobel Laureate Chair in Hydrocarbon Chemistry at the University of Southern California. He has 820 peer-reviewed publications and 14 books. He holds 100 patents and has many awards and recognitions, too numerous to mention in this forum. He will be speaking on the methanol economy concept to replace fossil fuels. Our second expert, John R. Bucknell, is the CEO and founder at Virtus Solis Technologies. John is a serial entrepreneur with 26 years industry experience in bringing mass-manufactured energy conversion systems to market, including 9 years of aerospace engineering, including design of the Raptor rocket engine for SpaceX. He will speak on synthetic fuel production through ocean thermal energy and a proposal describing co-production of electricity and synfuel with molten salt nuclear reactors. So, enough from me. If you have any questions for clarification, please raise your hand and we can go to them. Save your substantial questions for the end, and hopefully we can discuss them. At this point, I would like to welcome our first expert, Dr. Prakash.
Good morning, everybody. Good afternoon. It has been fun, participating in this forum. And we have been working on carbon capture and conversion to synthetic fuels for many, many years at the University of Southern California. And I thank you, Al, for the kind introduction. And may I have my first slide, please? Okay, the topic I'm going to discuss today is carbon dioxide capture and conversion, what we coined the term the methanol economy. Next slide, please. We have increasing world population, and of course, everybody wants to live like Americans, that is increasing standard of living. And the increase in standard of living has happened because of usage of fossil fuels in the 19th, 20th, and 21st century. Fossil fuels are nothing but oil, gas, and coal. In the chemistry term, they're made of hydrogen and carbon, two elements. They're called hydrocarbons. These are finite sources, and once it is depleted, they are non-renewable on the human timescale. And what's happening, burning all these fossil fuels with oxygen of the air, the carbon ends up as carbon dioxide, the hydrogen ends up as water. And this is leading to increase in carbon dioxide content of the atmosphere. And you all know that carbon dioxide traps heat and reflects heat onto Earth's surface, and the greenhouse effect is happening. This is leading to so-called global warming. You might have heard about this, all the ramifications of that. But if you really look at the concentration of carbon dioxide in the air, it's only 420 parts per million. In fact, a noble gas called argon is present in the air that's 10,000 ppm. But this small amount of carbon dioxide is very important. Without that, there won't be life on Earth. I'll come back to this a little bit later. Next slide, please. In the middle of the last, this thing, in 1650, actually, the world population was around 500 million. And in 2000, we surpassed the population 6.2 billion. In 2011, we surpassed 7 billion. And if you project to 2050, an optimist will tell you we may equilibrate around the world population 9 billion. If you talk to a pessimist will say it may increase to 11 billion. And what modern human beings do is they spend a lot of energy for many things, for example, heating homes, transportation, all kinds of industrial applications and all that. And actually, currently, if you compute all the energy used by humankind, you can put it in certain numerical terms, it's equivalent to continuous 18 terawatts. That is 18,000 nuclear power plants producing 1 gigawatt or 1,000 megawatt of electricity continuously. And this need is going to go up by 21 terawatts by 2025 and 30 terawatts by 2050. These are all some, proposals, okay? The numbers can change here and there, but these are some interesting numbers. Next slide, please. And if you really look at the energy, picture of the Earth, still in the 21st century, where in 2021, 75 to 80% of our energy that is utilized by humankind comes from combusting fossil fuels. I already mentioned fossil fuels are made of coal, oil, natural gas. And if you really, this is a data from 2014. And if you really look at it, still, coal is not, although coal consumption to produce electricity is coming down in the United States, countries like China and India are increasing, coal burning to produce electricity. And the natural gas production has increased in the United States because we have found a lot of shale gas, and natural gas is being replaced. The coal is replaced by natural gas producing, power plants. But if you really look at all the others, renewables, combustibles and all, it's only 10.3% of the total energy picture. Hydro is about 2.4% or 2.5%. And the nuclear has not changed very much. It's only 4.8%, okay? And if you look at Renewables include solar, wind, geothermal, ocean, that kind of nature. They're going up, but not at a fast pace to replace these fossil fuels. In fact, what are fossil fuels? Fossil fuels, I already mentioned, they're coal, oil, and natural gas. Natural gas is a mixture of methane, ethane, propane, these C1, C2, C3 containing molecular hydrocarbons. And when I teach undergraduate classes, I define fossil fuels are nothing but fossilized sunshine. It all derived from the energy of sun over eons, where plant and animal matters have decayed in the Earth's crust or mantle, and it was stored. If a process happened, and you created coal, oil, and gas at different depths. And there is also theory that these fossil fuels might have come by meteors and things like that. But the major people agree that fossil fuels were created by living matter, decaying living animal and plant matter. They were created over eons. Their use has given us unprecedented prosperity and growth to humankind, as we realized in the past couple of centuries. Next slide, please. Of course, all this fossil fuel burning, if you really look at it, we burn coal, we burn petroleum, we burn natural gas, we produce cement, we have agriculture, we have animal husbandry, gas flaring, all kinds of stuff we do activity. And in 2017, believe it or not, we are spewing 40 billion tons of carbon dioxide by so-called humankind activities. I call that as anthropogenic activities. That is 40 billion tons. And half of the CO2 emissions accumulate in the atmosphere, presently more than 20 billion tons per year. This contributes to global warming. The global temperature is going up by 1 to 1.5 degrees. Glacier ice melting, sea level rising, ocean warming, of course, leading to climate change, as the scientists are predicting. And dissolution of this carbon dioxide in the ocean results in making what is called soda water, the carbonic acid. And this carbonic acid, which we all drink, when you drink soda, this can destroy coral reefs, producing further carbon dioxide. Because coral reefs are basically made mostly of limestone, which is calcium carbonate. So this is another big issue we have, ocean acidification. Next slide, please. Now, if you really look at greenhouse warming gases, carbon dioxide is called the culprit, About 64%, this can vary again, depending upon who has done the science. I'm just giving you some approximate numbers. 64% of the global warming comes from carbon dioxide, anthropogenic carbon dioxide, And also there are other chemical compounds which create global warming. These are called halogenated compounds, and these are called freons, which are used as refrigerants. They also contribute, and they're slowly being, replaced. Then there are nitrogen oxides called nitrous oxides, which come out of, emissions of internal combustion engines and diesel engines and things like that. At high temperature, the engine operates. The nitrogen reacts with oxygen to form nitrous oxides, nitrogen oxides, which contributes to about 6% of the global warming. Then there is methane, which is a one carbon hydrocarbon, CH4, that is the molecular formula, which is a principal component of natural gas. That leads to 17% of global warming. And I have a little table here. I hope people can see this. If you think carbon dioxide global warming potential is 1, methane has a global warming potential of 23 times more global warming potential than carbon dioxide. And the atmospheric lifetime of methane is 12 years. So this is a big problem too. Look at nitrous oxide. It is 296 times more global warming, mole per mole. And the atmospheric lifetime is 114 years. So-called HFCs, the hydrofluorocarbons, which are being replaced as freons for your refrigerator, they're also very global warming. And they're also, for example, the fluoroforum, which is HFC 23, is 12,000 times more global warming than CO2. So these are, very difficult. So there are a lot of rules and regulations. The Montreal Protocol has been, passed to control so-called this hydrofluorocarbons. And even if you think about, a lot of these transformers have a fluid called sulfur hexafluoride, SF6. And that is 22,200 times global warming potential. So there are molecules which are much more, global warming, for example, than CO2. And they also linger in the atmosphere for a long period of time, okay? And of course, I already mentioned the CO2 dissolving in ocean, the acidification is also a major problem because it can destroy all the marine life. When the coral reefs go, lot of the ecosystem gets affected, okay? This is a big, big problem. Next slide, please. So one of the things that engineers and scientists have talked about is, why can't we capture this carbon, which is spewing out of your chimneys, for example, in a coal burning power plant or in a cement plant, or even from the air? Air is very dilute. I'll come back to this a little bit later. Can we capture this carbon and then bury it, for example, in depleted oil fields underground, or depleted deep aquifers, or depleted natural gas fields? Or can we put it under the ocean where it remains under pressure, it doesn't come back up? But these people have talked about, even they have done experiments, but it's a very expensive engineering experiment. It has been done, okay? Especially in Norway and Sweden, people have tried this experimentally. And still people are talking about it. First of all, to do this, you have to capture carbon dioxide very efficiently to put it away. And this itself, people are working on it. There are many technological processes are being developed. But as a chemist, as trained as a chemist, for me, carbon dioxide is a convenient feedstock to make synthetic fuels and chemicals. And if it can take carbon dioxide from these point sources, or even including air, convert it to synthetic fuels and products, then we can make carbon neutral fuels. Just like Mother Nature does photosynthesis, make carbon neutral products. Through chemistry, we can make carbon neutral synthetic fuels. And this is the thing I'm talking about. On the left side, I have a little thing called carbon recycling to fuels and materials. That's what I'm going to tell you, a little thing what we have done at our institute. And even these ideas have been commercialized on a small scale. Next slide, please. Now, just to give you a picture, ladies and gentlemen, what we are dealing with. I've given you a daily usage of fossil fuels here. In fact, humankind is consuming 95 million barrels of oil a day. You know how much a barrel is? A barrel is 42 gallons or 160 liters. So 95 million barrels of oil is consumed, making all this, gasoline, diesel, aviation fuel, aviation kerosene, bunker fuel to run your ships. Shipping industry uses a lot of fuels. And 10 billion meter cube of natural gas is burnt every day. And still, I think around 15 to 16 million tons of coal is being burnt. And all this activity is leading to more than 40 billion tons of CO2. Now, just to divert a little bit from here, in the United States, Brazil, and places like that, we have been also playing with another concept called the ethanol economy. Ethanol can be produced by fermenting sugar or converting starch of corn crops into, for example, ethanol. And ethanol, we talk about e-fuel, and there are vehicles running on the roads of United States which can run on ethanol from varying proportions with ethanol and gasoline mixtures. Even cars can run on 100% methanol. And if you really look at ethanol economy, about 13.9 billion gallons of ethanol is produced per year. This is equivalent to 330 million barrels from corn. So 40% of the corn crop is being diverted to produce 330 million barrels of ethanol a year. This is equivalent to 225 million barrels of oil, is 2.5 days supply. is a drop in the bucket, ladies and gentlemen. And also we are hurting the global food security issue. Food security for humankind is more important than energy security. So we'll come back to this in the next slide. In Brazil, 5.57 billion gallons of ethanol was produced, and this is converting their sugar crop into ethanol. People talk about vegetable oils, the biodiesel. Biodiesel made from vegetable oil, in my opinion, is not viable because to make, this vegetable oil, the nature works very hard to make a gallon of oil. If you look at the life cycle of converting solar energy and time and land and all the things you put together, biodiesel, in fact, does not make sense at all. It's, again, a drop in the bucket. Next slide, please. So just to elaborate more on this, people talk about, we are all here, you and I, all, human beings are here because of photosynthesis. Nature fixes CO2 by photosynthesis, taking carbon dioxide, water with this green dye in the leaves called chlorophyll, and sunlight converts to sugar-like molecules. And oxygen is also produced in the process, okay? And you can make, for example, all these fuels can be derived out of plant matter. Ethanol, I just mentioned. Even butanol can be made, vegetable oils. But this can only be a small percent of energy mix because humankind, with such a huge population pressure, we need land, availability and use becomes an issue. And of course, to grow plants, you need water. In fact, water is going to be a much bigger issue with global warming for humankind. Water resources, there will be fights over water. Irrigation becomes a big issue. Then we need to tackle, I just mentioned, the food security versus energy security issue. And of course, to grow crops, we need to put nitrogen, phosphorus, and nutrients, fertilizers, which are also made from fossil fuels. The hydrogen generated from fossil fuels is converted with nitrogen to make ammonia, and ammonia is converted to urea, and urea is used as a fertilizer. Of course, when you're doing biomass conversions, processing technologies, energy use, the whole life cycle, you need to worry about the overall energy balance. So if you really look at it, to make a grain of rice, ladies and gentlemen, from CO2 water, it requires time, it requires land, water. The overall life cycle, if you look at the energy efficiency, is close to 1 or 1.2%. Through chemical processes, ladies and gentlemen, we can develop straightforward processes to make synthetic fuels and feedstocks at much higher efficiency. But if you really, look at our world where we live in, the most energy that is coming to Earth is from sun. Sun is a nuclear fusion reactor. I hope we can replicate fusion, we are trying to do on Earth, and hopefully we will be successful. So sun is a nuclear reactor, which is this source of all energy on Earth, mostly Earth, past, present, and foreseeable future, next 4.5 billion years. Sun is going to be there. And sun is putting out continuously, incident on Earth is about, I just gave a number here, it's about 200,000 terawatts continuous. It's a reliable, safe nuclear fusion reactor. So we need not despair that Earth does not have an energy problem per se. We have an energy storage and energy carrier problems. All fossil fuels we talk about are energy carriers created by, mostly by sun's energy. Next slide, please. So this is another interesting slide I just picked out from literature. It's a newsletter published sometime back in 2015. And if you really look at the solar, the energy that is coming out in terms of terawatt years, solar energy is renewable in the sense every year we can capture because it's going to be there for next 4 billion years or so. It is 23,000 terawatt year equivalent. And if you look at the tide energy, it's only 0.3, terawatt year per year. Geothermal I have given here, the hydro, the biomass, and also the ocean thermal energy in the blue. And wind is also because of sun heating the air. Wind energy is 70 to 120, terawatt years. And the finite sources you can also compute in terms of energy. All the natural gas that is there in Earth is only 215 terawatt a year, non-renewable. Petroleum is about 240. Uranium, fissionable, is about 90 to 300. And coal is about 900 terawatt a year. These are all non-renewable. We have these other things in this big thing I have given, the renewable. So, what's the problem? The problem is, you can use, for example, solar energy to produce electricity. We are doing it. But solar flux is intermittent. We have solar energy incident mostly during the daytime, and nighttime we have sun is not there. So you need to store energy. And the battery technology, in fact, my group works on batteries. We worked on flow batteries. We work on, iron-based batteries, which are much cheaper than lithium, basically earth-abundant materials. But the battery technology is still infant. Can we use this solar energy or any wind energy, any electrical energy we can generate cleanly, not from fossil fuels? Can we take CO2, hopefully directly from the air, and water? Can we make a synthetic fuel? This is the question. Can we store this energy we can capture in chemical bonds, simple chemical bonds like carbon-hydrogen bonds, carbon-carbon bonds, and things of that nature? Then we have tiger by the tail. Next slide, please. Now, carbon dioxide, everybody makes it a villain. Without carbon dioxide, ladies and gentlemen, we have no life on Earth. Remember that. We cannot ban carbon dioxide, okay? Carbon dioxide has to be managed. Nature manages it. And CO2 is considered a very important synthetic feedstock. In fact, you make polymers out of it, so-called polycarbonates, polyurethanes, for example, your windshields and all that, car windshield is made with polycarbonates. It is used as a fire extinguisher. You all know about dry ice. It can be injected into metal castings. It's a respiratory stimulant we need for our respiration process without CO2, because we exhale CO2. But we need little bit CO2 to be present to have that breathing mechanism. It's an aerosol propellant, it's used in aerosol cans as a propellant. It is supercritical CO2 extracts caffeine from coffee to make decaffeinated coffee. All kinds of, for example, perfumeries, for example, from plants and all is extracted using liquid CO2. It's a chemical feedstock to make organic carbonates. You can make all kinds of lactones, pharmaceuticals, and things of that nature. Food industry uses, your carbonated beverages, beer, Coca-Cola, all your cola products and, things like that, decaffeinations. And also is used in greenhouses to increase the plant growth, because CO2 can make your, in greenhouses, can make tomato plumpier. Your strawberry gets bigger, with CO2. But CO2 can be also used to make urea, the fertilizer with ammonia. It's a $200 million ton product made worldwide, So this is another, interesting application of CO2. It's already utilized. It's used for oil recovery, natural gas recovery, coal bed methane recovery. But as a chemist, I can convert CO2 directly into methanol. That's the story I'm going to tell you. It can also be made to methane, the natural gas component, formic acid, dimethyl ether, dimethyl carbonate, liquid fuels. You can use it in fuel cells. You can also make plastics, synthetic hydrocarbons, olefins, and plastic. This is the story I'm going to tell you. Next slide, please. Now, people talk about hydrogen economy, you might have heard about. Hydrogen is a primordial molecule. It was when the Big Bang happened, after that, hydrogen was the first molecule to be made in the cosmos. Of course, hydrogen, H2, is very clean. It can react with oxygen to make water and produce energy. It is used in fuel cells. But hydrogen is not a primary energy carrier on Earth. It liquefies at minus 253 degrees, Celsius. That's 423 degrees Fahrenheit, minus 423 Fahrenheit. It is tied up in water and fossil fuels. It has to be liberated. It is incompatible with 20% oxygen in the air. It is a love affair with oxygen. It can take off, burn to make water. Only problem with hydrogen is liquid hydrogen has 1/3 volumetric energy density of gasoline. It's a very low density molecule. So it's not very convenient to store it and dispense it. 2 grams occupy 22.4 liters volume. So it's very difficult to contain hydrogen in quantity under pressure. And almost all metals which contain carbon, above 5,000 psi, pounds per square inch pressure, they become brittle. So you need to put a carbon, fiber tanks to store hydrogen at very high pressure. For example, Toyota Mirai uses a carbon composite tank where they carry hydrogen at 10,000 psi. It's a high pressure tank you're carrying in your car, in a fuel cell car. So these are all some problems you need to worry about. Infrastructure is very expensive because it's very light, it diffuses, and it also burns with a colorless flame. So you need to be careful with it, handling it, okay? So hydrogen has some issues using it to transport it, but still, for some applications, it's a very, very clean fuel. Next slide, please.
Before you move on, could you just clarify, when you say hydrogen is not a primary energy carrier, what do you mean by that?
Well, on Earth, primary means using it as, for example, like using gasoline or diesel, which can be transported. Hydrogen transportation is pretty difficult. And also even the pipelines, and people talk about the seepage. You think natural gas seeps, right? It comes out, but hydrogen can diffuse through a lot of metals which have carbon in it under certain pressure.
So it's not feasible to use it as a primary energy?
Yeah, and it's difficult, it's difficult. I'm not telling it's not impossible, but if you generate hydrogen at a source, you can use it directly. But to transport it, take it in a tank or a truck or a rail car is very difficult, okay?
Thank you.
It's very expensive. You need to change the infrastructure, let me put it that way.
It's an important point.
Yeah. Okay, next slide, please. So what we have proposed about 30 or 35 years ago in my institute, we have an institute dedicated to hydrocarbon chemistry at University of Southern California called the Local Hydrocarbon Research Institute, with my late colleague George Olah, who won the Nobel Prize in Chemistry in 1994. We developed a concept called the methanol economy. Methanol is a very simple molecule. The structure is given in the blue, CH3OH. It's a one carbon alcohol. It used to be called wood alcohol. If you take any wood and heat it, and then whatever distillate is coming, you got some methanol. It's a very well-known molecule. And methanol is a very high octane fuel. It's octane number 100. It's an incredibly good clean burning fuel for internal combustion engines, which uses spark ignition. It is half the energy density of gasoline, 15.8 millijoules per liter. And in fact, it was the fuel of choice for all race cars since 1950. All Indy race car circuits, some of you know that, used to use methanol, okay, in large quantity race cars. And methanol can also be used in what's called direct methanol fuel cells, which my group developed with NASA JPL in the 90s under a DARPA program. In fact, you can directly make a methanol air battery to produce electricity at about 45 to 50% efficiency, which has been commercialized. I'll tell you a little bit about it. And methanol can also be used to convert it to a compound called dimethyl ether, which I have given on the left side, CH3OCH3. It's a high cetane, clean burning diesel substitute. It also can replace LNG, liquefied natural gas, and LPG for all kinds of purposes. I'll tell you a little bit about that. And also methanol, we developed some processes in my institute in the 1980s, can be directly converted to ethylene and propylene. These are the two basic feedstocks to make all petrochemicals, including plastics. So from methanol, we can make everything currently, we make it out of fossil fuels. This is the idea. And if methanol is made from CO2, we can make every product which humankind uses, which we benefit out of, which we can't say, stop it today. We need plastics, we need pharmaceuticals, we need agrochemicals to survive, because we have developed all this for the betterment of humankind. Next slide, please. In fact, methanol in an internal combustion engine, because of high octane number, methanol air mixture can be compressed. You can get a compression ratio close to 15:1. Whereas diesel gives you 12:1. Methanol also has a higher flame speed, gives you higher efficiency. More importantly, ladies and gentlemen, methanol has a higher latent heat of vaporization. That is 3.7 times higher than gasoline. That means it can take heat away from the engine when it's combusting. That means you're not going to make much nitrogen oxides. The nitrogen oxidation is curtailed if you use methanol as a fuel. That way, you're not producing nitrogen oxide in your tailpipe, which is also a greenhouse warming gas. And also, methanol is a one-carbon alcohol. When it burns, it does not make much soot. Soot is a very important, especially 2.4 nanometer type, soot is very bad for you, for lungs and all that. Automobile pollution creates a lot of these, pollutants. So methanol is a very clean burning fuel, not making much NOx or particulate emissions. And methanol can also be blended with gasoline to different ratios. It could be used. In fact, in California, in late 80s, we practiced M85, 85% methanol, 15% gasoline in many gas stations. Then the oil industry came up with the idea of replacing it with an additive to gasoline called MTBE, you might have heard about, methyl tertiary butyl ether, which became a problem because of its smell. So methanol is already a known, transportation fuel. So I'll tell you a little bit more about that. And it is also safer than gasoline because methanol flames can be extinguished with water, where gasoline and diesel flames require foam. So if you're in an accident, water can extinguish the fires. Whereas gasoline and diesel, you need foam. So this is also a very good advantage. And methanol also could be used to produce hydrogen on site. I'll tell you a little bit about that. If you want pure hydrogen, I can reform methanol to make hydrogen on site. And methanol, since it's a liquid, boils around 64.7 degrees Celsius, it can be transported in the existing infrastructure. See, the way I'm going here, ladies and gentlemen, one of the biggest adopters of this methanol economy is China. China is using methanol, in race cars, taxi fleets, buses, their dispensing stations. And I'll tell you how China is making its methanol. It's not green methanol, but they're making it out of coal because they feel that they can curtail a lot of pollution by using methanol as a fuel. Next slide, please. Methanol blending around the world. Look at China. All these provinces in China, they're already using methanol. Israel has adopted some aspects of methanol economy. Iceland is using methanol for transportation because they produce renewable methanol in Iceland. I'll tell you in the end. And also India, my own country, where I was born, is adopting some aspects of methanol economy. Next slide, please. And also methanol could be used in compression stroke engines to replace diesel. There is some work done in MIT by Daniel Cohn. He has shown you can make a spark ignition methanol engine. A 9-liter methanol engine gives you 2,000 pound-feet of torque, whereas a 9-liter diesel engine gives only 1,300 pound-feet of torque. That means you can make your engine smaller. It can give higher torque than a conventional diesel engine. Okay, so this technology is already being utilized it's already experimentally proven with UOP trucks and things like that, experimentally with DOE support. And you can also use with methanol all kinds of other ideas that you can have a turbocharging phenomena by injecting methanol into a conventional engine. And also the exhaust heat can be used to methanol to reform it to hydrogen, and you can increase the efficiency. This work by Cohn shows that you can increase the efficiency of an engine by 55% by switching to methanol. Switching this diesel to methanol in some of these engines. Next slide, please. One of the biggest users of diesel are heavy bunker oil-like fuels, which are very dirty, used by the shipping industry. Shipping industry is using 370 million tons of fuel, which are heavy fuel oil and middle distillates that come out of petroleum oil processing. And these are the dirtiest fuel, ladies and gentlemen. When you burn them, you make sulfur oxides, you make nitrogen oxides, you also make particulate emissions. In high seas, nobody is caring about that. Next slide. So people are thinking about adopting methanol to replace this bunker oil. In fact, there is a company in Sweden called Stena. Stena is the second largest shipping company, and they have converted some of their ships, which used to run on these diesel engines, to methanol engines with very simple modification, and they become very green in the Baltics. So emission control area in the North Sea and the Baltic, there's a cost benefit of using methanol as a fuel, and they get much better in efficiency. And in fact, 4 Wärtsilä engines, diesel engines of total 32,000 horsepower were converted many years ago. Next slide, please. With very little modification. Before, the engine looked like that, and they put additional injectors in a higher efficiency in methanol mode. This has been done. So only minor modifications were needed to convert these diesel engines into methanol engines. And this is already taken off in about 20 huge ships. Methanex, which is the biggest manufacturer of methanol, is using methanol as a fuel in their trawlers. And Lloyd's of London has already blessed all this. It's all insured. Everything is coming into vogue. And Methanol Institute, if you go on their website, you can get much more information as methanol as a marine fuel. Next slide, please. Methanol can also be converted by a simple process. It's a dehydration, a bimolecular dehydration in the chemistry term. You can make dimethyl ether. Dimethyl ether boils around minus 24.8 degrees Celsius. It's almost like propane. And this is an excellent diesel fuel also. Clean burning. It's a high cetane number. You have an octane number for gasoline, cetane number for diesel. And 55 to 60 is very high cetane. That means your combustion process is very clean. Clean burning, low NOx, no SOx, and no particulate matter. It's already used in spray dispensers. It's non-toxic, does not form peroxides. It can also be used as a substitute for cooking, LNG and LPG. Easy to produce, ship, and dispense. It's already used for sootless flame for artistic glass blowing. So it doesn't blacken your glass when you use it. So there are trucks in Japan running on DME, buses in Denmark. This Volvo is one of the biggest users of this technology. And China, Korea, they're all doing this. Next slide, please. Now, methanol can also be used to produce hydrogen and CO2 mixtures by reforming. And you can feed that hydrogen in a fuel cell to make electricity. In transportation sector, there are companies coming into vogue where they can take, instead of putting hydrogen in a tank, they put methanol, they produce hydrogen on board, run a fuel cell with a small battery. These are called range extenders. A typical electric vehicle, for example, can give you 200 to 300 kilometers with, for example, with a one charge. But if you add a fuel cell and a methanol, you can go 1,500 kilometers, 2,000 kilometers. So this idea could be very useful for transportation of trucking industry, using methanol as a fuel, but you can still run a, efficient electric type vehicle using a fuel cell. So these are all happening as we speak. Next slide, please. Now, methanol, of course, you can produce 3 moles of hydrogen. So methanol carries 12.1 weight% of hydrogen in the liquid form. And our group has shown even we can produce hydrogen without producing carbon. We have developed a process called amine reforming of methanol. These are all chemistry. Only thing is, this produces pure hydrogen where carbon is trapped as urea. So this is very good. So you can take methanol to, for example, a hydrogen dispensing station. You make hydrogen, board, so you don't have to store it under pressure. Make it, dispense it. And whatever urea that is produced can be taken to a shop and a plant, converted back to methanol and amine. So this kind of ideas we have talked about, where transportation becomes very easy of the raw materials. Next slide, please. And of course, methanol could be used in direct oxidation methanol fuel cell. A fuel cell is like a battery. You have an anode and a cathode. And methanol and water can be oxidized with a metal called platinum ruthenium, noble metals, completely to 6 electrons and 6 protons and carbon dioxide. This can be coupled at the cathode to make water. So if you couple 2 redox reactions, you can get 1.2 volts of electricity. At this juncture, I just want to demonstrate this fuel cell. Can we go back to this thing, please? Can we stop it? And I
Yes.
want to, maybe I...
Yeah, I remember now.
Okay.
Thank you. You're full screen on the broadcast.
Okay, all
No,
right.
no, you're not.
Oh, it should be a moment.
Okay, this is the heart of a fuel cell. I'm just showing a polymeric membrane here. And you have two dark squares here. One is basically we have graphitic surfaces on either side. And at the anode, I have put some platinum ruthenium nanoparticles, which is oxidizing methanol at the anode. Cathode, I have platinum metal, which can reduce oxygen out of air. So oxygen hits the cathode, methanol hits the anode, and you connect two wires, you make electricity, and methanol and oxygen react to make CO2 and water. So this is basically a fuel cell, and this was discovered with collaboration with NASA Jet Propulsion Laboratory in the 1990s. And this whole technology has been commercialized, given to a company called Smart Fuel Cells in Germany, which licensed out of my university, and Caltech, which NASA is, the JPL is managed by Caltech. And this is used for power supply for soldiers in the field. There are devices that have been built which generates 70 watts to 5 kilowatts, where you can produce electricity using methanol as a fuel. And I just want to show you, I have built a little toy here I wanted to show you, which this membrane electrode assembly is between two polycarbonate plates. And the cathode has some holes, can breathe oxygen out of air. And here I have some methanol and water. So what I'm going to do is I'm going to take some methanol and water in a little syringe. So I'm doing a little experiment here, methanol and water. And then I'm going to inject into this little gizmo I'm just built. I'm going to inject it and see what happens to this little, it makes electricity at room temperature. So methanol could be used to make electricity. Okay, you can go back to my presentation. This will be running behind me. So methanol could be used to make electricity directly. Okay, so this has been commercialized. Next slide, please. And methanol can also be used for cooking. It's one of the cleanest burning fuels. In fact, I was born in India. When I was a little child, my mother used to cook using kerosene stoves. And kerosene stoves, when they burn, they make black smoke, very, very deadly. You had to have good ventilation to use these kerosene stoves. And in fact, in India, poor people in the villages, when they use in huts, it's very dangerous and it's not good for their, health. But methanol, it burns with a very beautiful blue flame. In fact, China has developed methanol for cooking. They use 3 million metric tons of methanol for cooking, and they have potential for 8 million metric tons. You might have heard about alcohol stoves too. So methanol is in fact, we are trying to, promote this into a lot of developing world as a clean burning fuel and safe fuel. Next slide, please. And methanol also used as a boiler fuel in China. There are 1,000 boilers which used to use oil or natural gas. They're using methanol. In India, they're drying tea in Assam using methanol, okay? Because it can be produced and can be used. Next slide, please. And in fact, in Israel, Eilat, they converted a heavy oil burning power plant in Eilat, which is a kind of a town in Mediterranean. A 50 megawatt power plant was converted to a methanol burning power plant, and the pollution level came down in Eilat, Israel. So Israel has already used for turbines. It's a very good turbine fuel, and many islands are considering methanol as a fuel to make electricity. And methanol could also be used in fuel cells. As I showed you, direct oxidation fuel cell. It can also be used in molten carbonate fuel cell, solid oxide fuel cells, and there are a lot of marine, 10,000 kilowatt gensets that have been built with methanol, okay? Of course, methanol as a cooking fuel will change. It's a game changer. And methanol traditionally has been used to make chemicals like formaldehyde, the particle boards, MTBE, methyl tertiary ether, acetaldehyde, acetic acid, vinegar, propylene, polypropylene, all kinds of, And methanol can also be fed to some organisms. It's not a poison for you and I, but not for small, bacteria and organisms. You can make tofu-like products, feeding methanol into these organisms. And ICI in England produced 100,000 tons of animal feed using methanol in 1960. Okay, I didn't discover that; it's already known. Next slide, please. And 98 million tons of methanol was produced last year. And half of it was in China. It's a chemical feedstock. So methanol, in my opinion, ladies and gentlemen, can be a one carbon solution for a one carbon dioxide problem. Next slide, please. And methanol can also be converted to two feedstocks of petrochemical industry, ethylene and propylene. And once you make ethylene and propylene, you can make gasoline, diesel, aviation fuel if you want, and you can make all petrochemical products, agrochemicals, fertilizers, pharmaceuticals, everything can be made from these products. Next slide, please. And China, believe it or not, in 2020, they're making 28 million tons of ethylene propylene through methanol. Whereas you and I in America make it through petroleum processing. China is making it through methanol. Why? It's an import substitution for them. Next slide, please. Now, how do you get methanol? Okay. Methanol industrially is produced from what's called syngas currently, synthesis gas, a mixture of carbon monoxide and hydrogen. It can be made from coal, fossil fuel, or natural gas. But you can also directly convert methane, which is principal component of natural gas, to methanol. You can also produce from gasifying biomass. You can make it from carbon dioxide directly, called reduction using hydrogen. Natural sources, it used to be called wood alcohol, very well-known compound. And methanol was recently discovered in enormous galactic methanol clouds. If you go in this cosmos, nobody knows the origin of it. They're a billion light years wide, I believe, and 460 billion kilometer in diameter near wherever there is a nascent star, there is a methanol cloud. As chemists, we have speculated the origin of it, even have published some peer-reviewed papers in this area. What's the origin of this and all that? But that's not important for our discussion today. Next slide, please. So, before I go on to the next slide, I would like to tell you that this year I was a co-author of a report sponsored by this International Renewable Energy Agency, which in Europe commissioned this report for us on renewable methanol, and the details are given here. This you can get it if you want, that link. And there we looked at what kind of methanols. Methanol is a simple molecule called wood alcohol with a formula CH3OH, but it can come in different flavors. Next slide. In fact, we started defining methanol in some kind of a color code, a brown methanol, gray methanol, blue methanol, green methanol. Green methanol is totally renewable. So you can have different degrees of greenery or different colors. And brown methanol is you make methanol out of coal, it's brown. Natural gas is also brown. Okay, you're using fossil fuels. Okay. So there is a various ways you can make methanol from biomass, which is totally green. Renewable electricity, it could be green or it could be a little bit gray. Natural gas is a little bit gray because it can be more efficient. Coal is totally brown, okay, because you're also producing quite a bit of carbon dioxide making methanol. So we came up with this schematics. It's a 177-page report. If you're interested, you should read it. We talk about the state of art in this field. Next slide, please.
Just before we move on,
yeah,
just a time warning. We'll try to keep this within about an hour, so you got about 5 minutes. If you can.
Okay, all right. I'll make it fast now. Okay. Next slide, please. So methanol can be made from syngas, which is carbon monoxide, to hydrogen. These are all known chemistry. And if you have 3 moles of hydrogen to CO2, the second line, you can make methanol and water. And of course, CO and water, there is a water gas shift reaction. I just put it there, but it's not important for our discussion today. Next slide, please. Other way, yeah. Methanol from methane is made from methane and water. You make it, basically, it's called the reforming at high temperature. Make CO and 3 hydrogen. That's how From methane, you make methanol. And you can also do partial oxidation, which is very difficult to do. And there's also what is called dry reforming. These are some commercial processes of reforming natural gas. Okay, let's not go into this right now. Next slide. And coal can also be converted to methanol. That's what China is doing. We have high ash content coal, which is very difficult for them to burn. So they gasify it. And for every molecule of methanol they make, they put 2 molecules of carbon dioxide into the atmosphere. So it's a very brown methanol. Not good. But China is demonstrating to us that methanol usage is very good. And if rest of the world adopts green methanol, we have tiger by the tail. So China decided to adopt methanol economy using coal as their raw material, because that's the material they had. And they can clean up their cities because the emissions are very clean. Next slide. You can take, for example, biomass and also gasify it and make methanol. Of course, biomass can be converted to what is called biocrude by processing, and this biocrude can be transported, gasified in a plant and to make methanol. But again, we don't have enough biomass to replace all our gasoline and petroleum pool. And this is, definitely is useful. Next slide. And ultimately, can we make methanol out of CO2? Carbon dioxide is considered a problem. It's a linear molecule, very stable, and it's only 420 parts per million in the atmosphere. And so we are looking at how to capture CO2, because it's with air, oxygen, nitrogen, argon, moisture, CO2, that's what is present in the air. So next slide. In fact, there are various ways to capture CO2. Technologies are available called absorption. You can cryogenics, you can use membranes, and you can use biological systems to capture CO2, algae, microbial systems, and all that. And next slide. Our group has utilized a silica-based material where we have put a polymeric molecule called polyethyleneamines. We mix it and make this free-flowing solids. And these things, next slide, capture CO2 directly from the air. We can pass air over it, and the CO2 is grabbed at room temperature. And heating at 80 degrees, I get CO2 back. And in fact, this chemistry works even in presence of moisture. In fact, it's very efficient in presence of moisture. Ladies and gentlemen, I not only capture CO2 out of air, I can also capture potable water from the air. So this could be a game-changing for humankind. Not only we capture CO2, we can also capture water. Next slide, please. So this is reversible. We have shown thousands of cycles with this material. Next slide. In fact, this chemistry has been commercialized for indoor air capture. In fact, an average human being in an enclosed space, releases 1 kilogram of CO2 over a 24-hour period. So in big buildings, when people start working, when the CO2 level goes up, they have to exchange within the buildings, outside air to inside air, which has to be conditioned. With our materials, which are installed in 200 high-rise buildings all over the world, we can save 30% energy costs for buildings. So we are making buildings greener by using our materials, by capturing CO2 indoor, and then we throw it outside, or we can give it to greenhouse plants and things like that. Next slide, please. And this is a company called Enverid. You can look up. It's an MIT-based company which have licensed our technology. Next slide, please. Now, the idea is, if you have green energy, electricity coming out of wind, solar, nuclear, whatever, we can electrolyze water, get hydrogen, we can capture CO2 by our technology, make methanol in one step, and methanol could be used to make all petrochemical products, use it as transportation fuel. This is what we call the methanol economy. Next slide. In fact, this is just, too much chemistry here, but believe me that our group has developed a lot of chemistry in this area. We can capture CO2 from air using amine liquids, sodium hydroxide, potassium hydroxide. Using catalysis, we can convert to methanol. Next slide. We call this carbon neutral cycle. We have developed all kinds of catalysts, homogeneous catalysts, heterogeneous catalysts. Next slide. Not important for this. And this, our paper made in the front cover of famous, journals. One part process converts CO2 captured from air into methanol. Okay, this we have already done that. Next slide. So water electrolysis. If you have electricity, you can easily electrolyze water. This is commercial again. You can buy 5 megawatt electrolyzers from the Chinese, make hydrogen, and you need about 50 kilowatt hours of electricity to make 1 kilogram of hydrogen, and hydrogen and CO2 can be easily combined to make methanol. Next slide. And in fact, we are practicing this in Iceland, Reykjavik. We take geothermal electricity, which is very cheap in Iceland. We take CO2 that is dissolved in geothermal water. And every day, this company called Carbon Recycling International is making 12 tons of methanol a day. And this, we named it after my late colleague, George Olah, the Nobel laureate. It's called the George Olah Renewable Methanol Plant. So it relates to 90% reduction in CO2 emissions. It has 97%, green in a way, this technology. So this idea is already working. And Methanex and Geely, one of the biggest car makers in China, have invested right now. You need about 40 kilowatt hours of electricity to produce 1 gallon of methanol. That is 11 kilowatt hours per liter. Okay. And methanol carries about 5 kilowatt hours. So it's about, quite efficient, this whole process is. Next slide, please. So what I told you, ladies and gentlemen, this unassuming molecule called methanol or wood alcohol can be made from fossil fuels. That's what people are doing right now. But it can be made from coal, of course. I just showed you biomass. You can make it. You can also make it from CO2. If you make it from CO2 and green energy, this is a fantastic idea. And in fact, carbon is considered a one carbon problem, CO2. Methanol is a one carbon holistic solution. It's called the KISS principle. Keep it simple, stupid, or keep it simple, silly. It's a bridge fuel in the short term and renewable carbon neutral fuel in the long term. And we can do it as long as human life is supported by Mother Earth. Next slide, please. In fact, all the green energy I have given here, utilization, recycling of CO2 from the air, we call this anthropogenic carbon cycle, mimicking nature's own photosynthetic cycle. This is called, we call the methanol economy. We can take electricity, CO2, and the ultimate source of CO2 is air. And the reason I want to capture CO2 out of air is, it's less polluted. If it's coming out of coal burning power plant, there is heavy metals, there is sulfur, nitrogen oxides, and things like that. Air capture, the pollution to, say, solution to pollution is dilution. CO2 is so diluted in the air that is, in my opinion, the ultimate source to capture CO2. That's what nature does. Through chemistry, we can do it, as our group has shown over the years. Next slide, please. And all this stuff I talked to you today is, in fact, we published our first book called Beyond Oil and Gas, the Methanol Economy, in 2006. And I just published the third edition in 2018. And in fact, this book has been translated into 5 languages, including Chinese, and the Chinese adopted this idea, lock, stock, and barrel. With that, I think I conclude my talk, and I'll be happy to answer any of your questions or some of your questions. Thank you.
Thank you, Dr. Prakash. That's very enlightening and quite interesting. So if anybody has questions, I'm not sure what the process is here. Can you raise your hand? Okay, there's a hand raised. Tim Rickman, did you have a question? Are these people allowed to unmute, Carl?
Yes, you may unmute yourself now.
So raise your hand if you have a question and I can recognize you.
Okay.
And
Tim here. I have got a question. Can heat from nuclear reactors be used to make the process more efficient?
Sure, you can. In fact, the methanol synthesis, you need some energy. And in fact, people were thinking of building a natural gas to methanol plant in Washington area, Seattle, Washington. And the energy they were thinking of using to make it a little bit greener is to use the hydro potential. And apparently all the export was supposed to go to China, and it was basically stopped. that production, that methane to methanol for Chinese export was stopped.
We'll talk a little bit about nuclear conversion in my presentation when we get to it. So hopefully we can get a little bit into that.
Okay, thanks.
I have a question for you. You're mentioning capturing CO2 out of the air to make methanol. That obviously is very difficult because it's so dilute. Like, how efficient is there an efficient way to do that?
Oh, it is, because we use amines. CO2 is an acid. It's an acidic gas. So it's a simple acid-base reaction. Have you heard about acid-base reaction? So if you have aqueous sodium hydroxide, bubble CO2 into it, you're going to make sodium bicarbonate or sodium carbonate, right? And if you put back acid, you'll have a lava flow, the CO2 coming out, right? Remember, as a kid, you did this with sodium, with baking soda and vinegar. You had this volcanic experiment we do with children, right? I did with my son and daughter when they were in
science
school.
fair.
So basically, CO2 is an acid-base problem. So if you have a base, nitrogens are considered bases, the lone pair on the nitrogen, so it can react with the CO2 to make what's called carbamic acid. And carbamic acid, when you have water around, forms ammonium bicarbonate. And ammonium bicarbonate are thermally less stable than sodium bicarbonate or sodium carbonate. So it can be, when you heat it, take it to, for example, 70 degrees, it reversibly gives you CO2 under pressure, so you can put it in a bottle. So I take 420 ppm that comes out of air, and I give you 95.5% CO2 under pressure in a tank.
Oh, okay, that's very good. Yeah. I see Stephen Ignetti has a question.
Okay, you hear me?
Yes.
Okay. Actually, it's his dad, and you can't see me. But my question, I saw it, it's on one of your slides, it's $1.80 a gallon of methanol.
4 cents a kilowatt hour.
Oh, okay. Well, like when making gasoline or jet fuel, how competitive is the price?
It is, in fact, in methanol to gasoline, there's a MTG process which was developed by Exxon in the 1970s. In fact, in New Zealand, there was a plant. They were making methanol and converting it to gasoline. Over zeolites, you can do this. So all this chemistry is available, and chemists know how to do it. Especially making aviation fuel is not that difficult.
Even from CO2, even if you do it from
exactly. CO2. In fact, if you go and read the primary literature, there's a lot of work going on how to convert CO2 and hydrogen directly into aviation fuel, how directly into diesel. These are all happening. Chemists are having a fun day doing this.
It's competitive.
We can make it competitive. Competitive, again, it depends on the cost of producing hydrogen. Electricity prices too, it's time dependent. For example, at certain periods of time, electricity is given away, especially wind energy at night, you can get it for nothing. They want to take it away. So you need to, in a distributive generation ideas, if you should make hydrogen production and do all this. So you need to think differently. But the beauty of what I'm talking about, you can keep existing infrastructure. How important it is important. Everybody talks about electric propulsion. To put 1.2 billion cars, IC engine cars into electric cars, how much carbon you're going to put? Nobody does the life cycle analysis here.
Indeed, and especially the waste and all that.
Exactly.
Colin, Megson has a question, I believe.
Colin, you should be able to unmute. Go ahead.
The green hydrogen economy is an absolute juggernaut at the moment, and it will bulldoze any form of competing energy economy, certainly out of transport, out of much of heating, and out of some industrial processes. And I can see methanol being used in the industrial processes for the manufacture of all the chemicals that we need. But I think green hydrogen will just be unstoppable from now on.
Yeah, but the thing is, these are what the governments are talking about. But I don't think really people have analyzed it. Even the electric vehicles, people talk about it. Even Biden administration says we are all going to go electric. The bottlenecks are difficult. Okay, if you have green hydrogen, it's a no-brainer. In fact, methanol is nothing but it's a disguised hydrogen. It's so easy to liberate it, so easy to transport it, and in fact, China, you can buy $100 kit to convert a Toyota Camry, which runs on gasoline, to 100% methanol. And it's already done in China. China did it because necessity is the mother of invention for them. And the Western world should also be thinking out of it. We should come out of this affluenza mode. We are too affluent for our own bloody good, I think.
The other
could I just say that the US now have a green hydrogen plant to get green hydrogen down to $1 per kilogram.
Oh, then we can make methanol a lot cheaper. Transportation fuel, very cheap.
Yeah, but the other thing is that it's only been announced today about another major company coming out with hydrogen-fueled internal combustion engines. So that will be probably a strong contributor.
Sure. Look, I look. The things will definitely happen. What I'm trying to tell you. I hope you don't mistake me. That there are a lot of technologies that can be adopted, and methanol economy is a concept which can benefit us right now. Okay, in terms of not changing infrastructure, and also the possibility to make all the products of petroleum oil. We currently make it of fossil fuels. Okay, so this is, in my opinion, very important. I'm not telling hydrogen there will be some penetration and all that. For example, look at Toyota Mirai, right? That you're riding on a 10,000 psi a carbon composite tank. Okay, luckily we didn't have electric vehicles had more accidents than fuel cell vehicles. Okay, that's true. But again, if you start using there are things which people are not looking at. Carrying hydrogen on your back has a lot of issues.
I think we're going to have to cut off the discussion here. We have another speaker, and time is running out. So I'd like to switch over now to introduce John Bucknell, who will be speaking on synthetic fuel production through ocean thermal energy and a proposal describing co-production of electricity and synth-fuel with molten salt nuclear reactors. Welcome, John Bucknell.
All right, great. Can everyone hear me? I think I'm unmuted.
Yep.
Yes.
All right, thank you for the introduction. I'm going to rerun through some of the items that Dr. Prakash discussed and talk primarily about economics. I mean, all these energy storage ideas that are floating around are primarily challenged by the economics. The $1 per kilogram hydrogen is a dream at the moment. Those Toyota Mirais, if you've driven them, they're about $14 a kilogram is what you pay today. And most of the challenges with energy storage are around the economics. And those are the things I'm going to address. I'm going to draw from 2 prior publications I've made. You can find these online on ResearchGate or otherwhere, and we can talk about that in some detail. So with that, my topics are the mechanization of those energy storage and some economic analysis around that. So next slide, please. All right, so in general, if you had sources of energy, electricity is the source that you would want. It's very easy from many different mechanizations to transmute it to one form or another, to transmit it to heat, to motive force, to light, to many other forms of useful energy. However, the challenges with the storage are that it's very heavy to transport that electricity and takes a lot of room compared to alternatives. And transport in particular, especially the heavy duty cases, which I'm going to say marine, rail, aircraft, trucking, are infrastructure that are very challenging to convert to primarily energy use through electricity. So those would prefer to use existing infrastructure with a drop-in replacement. Next slide, please. And as we were saying earlier, primary energy source, that's, again, where the energy comes from, is, as of last year, still 85% natural, sources of fossil fuels. And by sector, transport is a good quarter of that. that needs basically fossil fuels converted to gasoline or diesel fuel to be used to get things around. And transport is a large underlying aspect of basically the entire economy. So let's talk about that in detail. Next slide, please. We've talked about decarbonization in general for a lot of reasons. For the fossil fuels, there is a lot of mortality related just to the production of that fuel, digging it out of the ground, processing it, getting it to the power generation. So this is an interesting graph that shows you the relative safety in direct deaths or deaths from pollution related to all the different energy sources that we use predominantly. And you can see that nuclear in particular has had an amazing safety record. And solar's only challenge is related to primarily rooftop installation for residential and people falling off the roof. But it's not zero, but certainly far, far less than the fossil fuels that we have today. Next slide, please. As we were talking about, transport is underlying all the global economy. And storing via batteries is a problem because you lose huge amounts of payload in your transport vehicle. And if you look at the emissions from using fossil fuels, and these are normalized across all of them between the different forms of heavy-duty transport, if you can go fast or carry a lot of cargo, and you can see that shipping is so much smaller than the balance of methods. The vast majority of transport of goods is via marine use. And if we were to convert, for example, one of these large cargo container ships, more than half of that payload that it can carry across the water would be just carrying its batteries if we were to use the battery densities we have today in automotive. Next slide, please. We talked about this a little earlier, but the energy density of batteries in particular is very, very poor compared to chemical energy storage that we have available today. Supercapacitors are also very poor from a mass and density perspective. So again, liquid fuels make a huge difference, even though on the next slide, we'll see that methanol isn't as good as existing gasoline, but there are very good reasons, as Dr. Prakash talked about earlier. Next slide, please. We talked about all the reasons why methanol is good. It's about half the density of gasoline on an energy basis, but its cost is acceptable, and it's a precursor and is the underlying element of a methanol economy. So next slide, please. So we said that it's very easy chemically to synthesize these fuels, and of those fuels, some of them need some oxygen, but you just need a energy source, whether it's thermal, electrical, or even light for photochemical electrolysis. But the biggest challenge is those economics. In fact, extracting the hydrogen is the biggest cost today. And we talked about the cost of hydrogen, even extracting it from natural gas for use in your fuel cell vehicles today. And even the best ones are very expensive. The carbon dioxide, on the other hand, is less challenging from an energy perspective to extract, but we're going to talk about some solutions. So next slide, please. This is a slide I think I've stolen from the methanol economy. I've added one other arrow. You can see that there's all sorts of processes to get from carbon dioxide and water and get it into a combustible product, which is hydrocarbons, alcohols, and so forth, and get it back into CO2 and make a circular energy economy. The one thing that I've added on the left is that the CO2 in the atmosphere and the CO2 dissolved in water are in equilibrium. In fact, that 70% of the Earth's surface that is covered by water is in direct equilibrium with the CO2 in the air. So if you want more CO2 in the air, the sink is going to be the ocean and vice versa. And that is a temperature-dependent process. And in the warm ports of the ocean, the CO2 comes out of the water, and the cold ports, it's absorbed. So there is a concentration of CO2 in water, not primarily in the ocean, but also in freshwater sources that we're going to use for some mechanizations I'll show in the next couple of slides. Next slide, please. So the two I'm going to show examples of are some things that I've published in the past. One's called an ocean thermal energy cycle, and the reasons for that you'll see as I talk through it. And then using a heat source, primarily nuclear, for that, taking that excess energy and converting it to fuels. One of the bigger challenges with chemical processes is that they don't like to stop and start. If you have a renewable energy source like wind or solar, and it comes on a third or a quarter, or even half the time, and shuts off the other half, your localized chemical energy factory consuming that energy doesn't like to turn on and turn off in a switch, primarily because of thermal inertia. So you'd like to have something that has energy continuous. So those assets are being producing their products on a continuous basis and most efficiently as well. Next slide. Okay, so this is a bit of an eye chart, but the ocean thermal energy cycle is very interesting for a number of reasons. Number one is extracting solar energy from the heated water at the surface and running a thermodynamic cycle based on the cold water at depths of about 1 kilometer and producing electrical power through what's called a Rankine cycle, which is a thermodynamic cycle. You get hydrogen and oxygen out of that, and also carbon dioxide through a process I'll describe in a little bit. And then there's many ways to get methanol, methane, or higher order hydrocarbons in that same plant. And in fact, the upwellings in the deep ocean, where the nutrient-rich water from the deep is brought to the surface, are the most productive parts of the ocean aquaculture, which produces small phytoplankton and plankton, and then larger fish and larger marine animals. And in fact, something like this could be actually carbon negative, because all those animals that grow and are consumed and then die and fall to the depths are a natural way to store carbon. So those can be carbon negative on these processes. Next slide, please. This is something that we've talked about in the prior presentation, so I'm not going to go into very much depth, and I talked about aquaculture, so we're going to skip ahead in the interest of time. So one of the bigger things, and we've talked about how to get CO2 out of the atmosphere, and if we argue that the ocean and freshwater are in equilibrium, that dissolved CO2 in the water can be extracted. In fact, the U.S. Navy has had a device that they've called continuous electrodeionization cell, which allows us to extract CO2 and hydrogen, frankly, directly from fresh water and seawater. So that is a great way to get that 76 to 100 ppm of carbon dioxide out of the water directly. Next slide. Okay, so another eye chart, but the long story short, you can take the thermal energy from seawater and convert that electricity at about a 5% conversion rate. Now, you would argue that that's terrible because it's so poor conversion efficiency, but the important part is the cost per unit of conversion, and that's the infrastructure that you have to build. The methanol plant itself is not bad. It's about 40% conversion efficiency from that electricity and thermal energy, which there isn't a lot of. But you do get fresh water out of it, and you get methanol directly in this chart. So let's talk a little bit more about this. Next slide, please. Oh, I'm sorry. I had something else in another deck. I apologize, but that is a relatively efficient plant. And a few years later, I came up with yet another way to get the synthetic fuels for even more efficient. And this is where we introduced the concept of molten salt reactors. Nuclear reactors use the only non-solar source of energy on this planet. It's the fissionable fuels came from supernovae a long time ago and are stored throughout the planet. In fact, there's good reasons to believe that when the moon was formed, that's how the fissionables got stored near the surface. Molten salt reactors are great because they operate at higher temperatures than pressurized water reactors. And thermal systems want to do the greatest temperature difference between the source and the sink. That's called the Carnot cycle. So the systems that run at the greatest temperature difference have the greatest ability to convert the thermal energy available into mechanical work, which is what this system is doing. It takes the molten salt, which runs 6 to 7, even 800 degrees C, and that heats up a noble gas, in this case helium, and runs a thermodynamic cycle on it. And you can find this in a YouTube publication. If you search me on the internet, and we'll talk about that a little later, then use the offtake from both thermal and electrical energy to make hydrogen and then methanol. And you can see that these overall efficiencies are very good compared to the prior system. So let's get on to the next slide and talk about why the high temperatures are important. This chart is the work of the Idaho National Labs, who's been working on nuclear power and its uses for a long, long time. And you can see that the conversion efficiency of hydrogen is the most important metric, and that's why we've chosen molten salt reactors as the use case, because we want to be able to get that source temperature as hot as possible. The dark blue is high temperature electrolysis, which can get over 60% efficient at 1,000 degrees source temperature, which is possible with molten salt but not pressurized water. I actually discovered this after I wrote the prior paper that you just saw, that used a sulfur iodine cycle, but those are very similar at 1,000 degrees C, but the high temperature electrolysis is better at lower source temperatures. So in general, 60% of conversion efficiency is fantastic in the grand scheme of things. That's why we've chosen this cycle for the Synfuel mechanization that I'm showing you.
So
okay,
before you move on,
sure.
Just a quick question. So using the high temperature from nuclear, you're allowing yourself to get more efficiency. If you're using other methods of green hydrogen, I'm assuming are like cold, like 300 or 300 Kelvin kind of thing.
For the most part, it's straight up electrolysis. So your conversion efficiency, it's whatever you're getting from sunlight to DC, which the utility scale is 19 to 20%, and then of that 20%, you're maybe 70% at best for your straight electrolysis. So a combined system where you have thermal energy available, you're very, very good. So a photovoltaic-based system would need to use some of that photon energy from the photovoltaics to create heat to do the electrolysis. So the conversion process is much more efficient.
What time are you eating?
Sorry, I couldn't hear the question.
I think it'll be about another half hour.
Yeah, we're gonna find and mute. Sorry, Colin.
Sorry.
Just go. Please go on.
All right. Al, did that answer your question?
Yeah, I'm not quite sure I followed it 100%, but effectively this high temperature is much more efficient than just regular electrolysis by
That's
like
correct.
a factor of 2.
Yeah, that's correct. Okay, so let's get in the next slide. And this is where the economics comes in. These systems that I've shown you have a very varied analysis to figure out what is the best. And levelized cost is a methodology to extract your return on investment. It takes however much you put in capital, however much you're putting into consumables or operation and maintenance, and then divide that by the energy you're getting out. So we're putting it all in units of megawatt hours. And in fact, the nuclear power plant that I showed you can produce electricity, or it can use that energy to generate fuels directly. And you can see that using the plant just to make electricity, you can get about $30 a megawatt hour, which is 3 cents a kilowatt hour. Or you can use it to produce energy storage in the form of hydrogen, methanol, or even gasoline. And you can see at the bottom row, if it was all just producing fuels, those costs are relatively low. And that's paying for a very expensive nuclear power plant to start with. The ocean thermal energy cycle is also pretty good from a cost perspective. And you can look in the notes in the bottom that the methanol goes from $50 a megawatt hour when you're still paying for the plant over that 20-year cycle to when it's paid off, it goes from $53 a megawatt hour down to about 13. So very, very inexpensive. So that's a very, very small price to pay. And you can see that compared to retail prices this month, actually, the electricity prices, which is a portion of the total electricity price you pay, are very much competitive. So these systems are all intended to replace across the board the existing infrastructure and provide low-cost systems that provide energy to those systems that need it. So I believe I have one more slide.
Just before you go on again, a question on that. It looks like you have costs going up as the capacity factor increases.
Can we go down?
Go to the next slide, please. Yeah.
Yes. So this is splitting the electricity and the methanol generation or the energy storage into two systems. So if you have 90% capacity factor in electricity, you can't use it to make the energy storage. So 0% on the electricity is 100% on the energy storage. So I apologize, that chart need a little bit more explaining, but I was trying to go quickly so we give as much time for Q&A.
Thank you.
Thank you. Okay, I think that was my conclusion, my slides. I think I wanted to present one more fact about primary energy. At the moment, for reference, those of us in the West consume about 9 kilowatts of primary energy. Every man, woman, child of 330 million of us in the US. Worldwide, that average is about 1.8 kilowatts. So if you would argue that we're barely okay in the West, most of the rest of the world is living in energy poverty, only using 20% of what you use. And of that 10 billion of us, roughly a billion and a half, maybe even 2 billion are using zero. So it would be great if we could get low-cost sources of energy to everyone so that we can use those as levers for universal prosperity, which is the point of my other business, which is completely unrelated, but there is tangential involvement with synthetic fuels if you can get low-cost electricity. So thank you for your time and attention. I'd be happy to take questions along with Dr. Prakash about all of this.
Thank you very much, John. That's a great presentation. And again, here we have just a reminder about Stand Up for Nuclear for everyone who wants to come out and support nuclear power. So we'll field questions. Just go to my participants list again. Raise your hand if you have a question for John. Gabe?
Sorry, I let Tim unmute himself. He was the first.
Okay.
Okay, I'll be quick. Just to clarify, if there were a conventional nuclear power station, like not a high temperature one, the sort of thing we already have, and it were doing as they do, making as much electricity as possible and as little waste heat as possible, would that ratio of heat to electricity, how would that fit making methanol or hydrogen? Would it have a surplus of heat or a surplus of electricity?
Let me see if I can come at the answer. So pressurized water reactors about 30 to 35% thermal efficiency. So they're taking 35% of the thermal energy that the nuclear power plant is creating and creating mechanical work, and then 98% of that is going into electricity. Those conversion processes that would make methanol are less efficient at that 200 degrees C, maybe less operating temperature, maybe 300 if you're lucky. So you lose on the energy conversion from the electricity portion, which is necessary for the electrolysis, and you lose on the chemical synthesis as well. So the yields of those plants, the ones I've showed, are 50% or more conversion efficiency on methanol. Conventional pressurized water reactors would be 30, 25%, somewhere in that neighborhood. To make it clear, and the capital used to build that synthesis plant is what you're having to pay for. The advantage of most of the nuclear power that's available today is it's already paid for, and you don't have to amortize that cost.
Okay, right. Thanks.
We'll go to either Gabe or Stephen Ignetti.
Yeah, it's me. It's Gabe Ignetti. I'm on two things here. A couple of things. The molten salt reactor is being built in China already. They're building a reactor. So I'm wondering first if that pretty much means that that we're going to be seeing these things commercially. And the next question is, I was confused about that chart because it said that OTEC had a cheaper price of gasoline or methanol per gallon than a nuclear power plant, but yet the cost per megawatt was higher for OTEC, even though it had a lower price per gallon. That seems like a contradiction. So that was like 2 questions, and that's all.
No problem. So just to answer the second one first, if you look at the 0% row, look at methanol, they're both more expensive for the OTEC plant. So that column there and then the middle column. So hopefully that answers your question, Gabe, on why the nuclear power plant is more favorable. It's more efficient from a cost perspective. Okay. The larger question about molten salt reactors, molten salt reactors have been around as an idea for a long, long time. It was the early 2000s that they were proposed because the ability to use thorium is a big deal. Thorium extends the fissionables available to our species by several orders of magnitude, allows us to run a nuclear if we wanted to forever. You can't use thorium in conventional pressurized water reactors. You need something else. Thorium reactors are primarily a chemical process, and having liquids that you can move around instead of solid fuels makes the chemical process even possible. So the Chinese have been working on it since the early 2000s because of the efforts here in the US to find out alternatives to leverage those solutions. I believe the one in China is not using thorium. So it's a multi-step process. There's issues with regulatory permissions, but there are test pilot plants being built in several places. A lot of activity at the Idaho National Labs as well, which is studying this. I believe there's also a plant being built there. So it looks like it's coming. We don't know the economics yet of these molten salt reactors. The estimates I made are based from the best published data available, but the potential is to very, very low cost because you basically consume almost no uranium and don't need to enrich it like existing facilities do. Hopefully that answers your question.
Great.
Okay, Phil?
Yeah. Let's make sure that I can let him unmute. There we go.
Hi. Yes, I am wondering about, in terms of replacing all of the liquid hydrocarbons with synthetic ones instead of from fossil fuel. My question is, let's say you switched out an oil refinery in, let's say, Houston with a synthetic fuel plant. Is the concentration of carbon dioxide in either air or water, is it enough so that you don't have to go through like insane amounts of mass just to harvest a little bit of carbon dioxide? Because I'm confused. Like I'm concerned that you won't be able to like physically sort out the carbon dioxide from the other water, oxygen, the other constituents of air. Like, what I'm trying to say? Like, you'd have to move so much matter to just take a little bit of carbon dioxide. Do you think that that's an upper limit problem?
Surya, why don't you take this one?
Just a moment. I need to ask you to unmute yourself. There you go.
Okay. It's a very good question. Actually, for making renewable fuels and products, I think we may be using maybe close to 900 million to 1 billion tons of CO2. But there is so much other CO2 coming out of other activities. So you have a very good point. The only way we're going to reduce the CO2 is by sequestration. So sequestration is a big thing and it needs to be done. And there are technologies coming up. As I said to our moderator, Al, CO2 is an acid-based problem. Okay, if you have a basic media like sodium hydroxide or calcium oxide, you can trap CO2. In fact, X Prize had proposed, done some projects where you can even put CO2 into cement. You can trap cement and things like that. So there are a lot of other technologies we need to use. The greenhouse problem we won't solve by making just synthetic fuels. The synthetic fuel, the reason we want to make it is, renewable synthetic fuels is we keep the existing infrastructure. So we don't. That's what we are trying to say.
And just to follow up on that, Phil, you're right. It's going to take a lot. But if you think about it, the reason the concentration of CO2 in the atmosphere is rising is because the combustion of fossil fuels is greater than any of the things it can take care of. Now, the good question is if you look at the carbon balances, how much is going into plants? How much is that sink absorbing versus how much the oceans are absorbing and the air absorbing? Because I think the oceans are far, far higher than the air because of there's so much of it. So I don't think there's any solution to extracting a trace gas from the atmosphere or the water. There's no other solution other than moving a lot, and the cheapest way to do that is the key.
Because I mean, as far as I'm concerned, if we are to get out of the net emissions added problem, there's no choice that we have but to synthesize huge amounts of synthetic carbon, hydrocarbon fuels. I don't know if you guys agree with that.
I 100% agree with that.
Yeah, I agree with you. Yeah,
Great.
we need to.
Let's if I don't mind, I see Kurt hasn't spoken yet, so I'm going to start with Kurt, and then we'll get to Colin before I chime in with my questions.
Okay, thanks. Can you hear me?
Yes.
Okay. What's the major pros and cons of converting hydrogen to methanol versus converting hydrogen to ammonia?
Okay, the hydrogen ammonia, the Haber-Bosch process is a very high temperature process. Where nitrogen and hydrogen is reacted at very high temperature with iron-based catalysts. And ammonia can be made, but ammonia, I think there was a question in this, maybe I'll answer this. Ammonia, of course, is a part of so-called nitrogen economy. People talk about that, how we can do that. But ammonia is a very toxic gas. Boils at minus, 25 or 26 degrees Celsius, 28 degrees Celsius. And it is very toxic to human being. If a whiff of it will incapacitate you. And also ammonia as a combustion fuel, people are talking about. In fact, some of the Arabic countries, the Middle Eastern countries, are thinking of making ammonia from natural gas, using hydrogen from natural gas and ammonia. But ammonia, when you burn it in an internal combustion engine, you also make a lot of nitrogen oxides. In NOx gases, which is again global warming. So ammonia, can be made, but CO2 and hydrogen, we have heterogeneous catalysis, which happens around 220 degrees Celsius under 50 bar pressure. But we have developed processes using homogeneous catalysts, which happen at 100 degrees Celsius at 70 bar hydrogen pressure. We can make methanol at very high, at 95% efficiency. Because there is a thermodynamic problem for efficient conversion with CO2 and hydrogen. Because, but this, we can, going lower temperature, you get higher conversions. Okay,
and I'd add about the production issues is that as a transport fuel, ammonia energy density is very poor. It's worse than methanol. So that's another challenge, is that the lower density you make your transport fuel, the worse your transport becomes. So, not the best solution from a transport fuel perspective.
Colin, I'll go ahead and unmute you. If you're there, Colin.
Hello, yes.
Hello.
There's two aspects, really. First of all, talking about molten salt reactors, other than the Chinese one, we certainly won't see any in the West for at least 2 decades. And even then, they may not be competitive with existing small modular reactors for electricity production. And the use of thorium is just a sort of sideshow, because molten salt reactors can run on uranium, and uranium will be available for the use of mankind for all of eternity. So that molten salt reactors become a sideshow. But the other thing is that green hydrogen production is attracting commercial investment by the billions of dollars in dozens of nations around the world, and it will completely displace liquid fuels in the transport sector, certainly for transports on the roads, and probably railways, and probably shipping either as methanol or ammonia, and even the prospects of it being used directly for aircraft. So it will just reduce methanol to the production of synthetic fuels for particular applications, and also for the production of all the chemicals that we need. So I think green hydrogen will probably be one of the blocking mechanisms that will restrict the production of methanol.
Can I take this one?
Go ahead.
Thanks, guys. Colin, you're identifying a couple of different factors, and certainly the point of this whole discussion is the economics of all of this. And picking a winner at this point is a challenge, but generally the most economic solution is going to win. The reason that green hydrogen is going so strong at the moment is two reasons. One is the inability to put more renewable energy in the grids that have lots of renewable energy. The penetration of solar in particular is a challenge because as you build more capacity, you can't use it. And so they have a lot of excess, especially in the regions that have a lot of solar. And the green hydrogen, the reason so much money is going into it at the moment is to try to utilize those solar assets to electrolyze water to create hydrogen. And the question is, what are they doing with that hydrogen? They're not putting it in transport vehicles. They're blending it with natural gas and natural gas pipelines to fuel natural gas-fired power plants. That's where all of the green hydrogen is going. It's not going into transport. And in fact, the mechanical solutions, and the reason Surya and I are talking about methanol, is that the mechanical solutions of gaseous or even liquid hydrogen, which are even worse, as a solution for transport, is miserable from a cost perspective of manufacturing the vehicles and having any useful range. Like a liquid hydrogen, even a liquid hydrogen aircraft would be more than half hydrogen to fly passengers across the world.
Methanol economy is a disguised hydrogen economy. You can think like that.
Yeah,
the best way to store hydrogen is in carbon, guys.
That's correct.
Yeah.
So I'll go ahead and butt in. In Washington State, near the south end of this state, we have had activists work very diligently to block the construction of a methanol plant there. Does this have an overall net climate benefit? Does it have an overall net local pollution benefit? And let me put some context in there. If, for example, existing fossil fuel generation plants and other point sources of pollution like shipping, like diesel and gas vehicles, were converted to methanol, even if this methanol plant were fed with fossil fuel stocks, would the completion of this methanol plant most likely reduce local pollutants and benefit the climate, or would it still be a possible cost?
Actually, this is a very difficult question to answer. It's a very important question you have brought up. Of course, the way the methanol plant in Washington was supposed to be, the Chinese had made a deal with the Canadians to get, the natural gas, a million BTU around $1.20 or something. And they were supposed to make methanol and ship it to China. All the methanol was going to China. Okay, that's what it was sold. This was several years ago. And this has been opposed. And also, whenever you use natural gas to methanol, of course, the natural gas seepage can also result in greenhouse problems too. I already told you, natural gas has to be handled very well. If there is a seepage, you also, result in this. So the methanol that was produced in Washington is not even considered of being used in transportation in America. It was all for export purposes. And just to make another point, all the flex fuel vehicles that are sold in America, which uses ethanol, they're also methanol compatible, but the original the equipment manufacturer is not giving warranty. These are all warranty games too. The car manufacturer should warranty not only for ethanol but also to methanol. They haven't done that yet. So US has to do a lot of those stuff before it really, these experiments can be done. Having said that, California ran in Los Angeles County a very successful ME85 program in late 80s, which was a success. But the oil companies basically didn't want to pursue this. They came up with this MTBE gasoline additive, oxygenate, where methanol went into making method tertiary ether. So there is a lot of political and other things here. We have no time to talk about it.
Yeah, rational policy is lacking.
Yes.
Thank you for helping us get there. Chris Bergen.
Hi, first I wanted to say excellent talk, lots of great information. Also, I had a question on, is there a half-life to methanol sitting in a tank or something? Like my motorcycle, I'm supposed to add a stabilizing agent to it when I store it for winter time. So how is methanol?
Methanol, once it is stored, it doesn't, it can be kept. It's it's forming peroxides is also not that high, so it is quite safe actually. Methanol is quite safe, and also methanol with some, it may take up some water, so that could be an issue. But a little bit water is not going to hurt you. And methanol water, you can separate it by distillation. They don't form azeotropes like ethanol and water. So methanol has all the advantages actually.
I have a follow-up question. If is that good, Chris? Okay. A question on deep decarbonization. I know if you think about deep decarbonization, you think about industrial heat processes.
Yeah.
What do you think is the best way to decarbonize industrial heat? This is open to either of you. Is methanol a solution? Is hydrogen a solution? What's the solution for these coal burning plants?
Cheap electricity is my answer.
Yeah, renewable electricity or cheap electricity. Okay, that's what I agree. Green electricity. That's the solution.
Yeah, because the conversion efficiency from electricity to thermal is very high, high 90s. So you can run a resistive element and get all the heat you need. The problem is that the energy sources to do that have been too expensive from an electricity perspective. So you burn fossil fuel, you get a lot more heat, you're not converting it. So if you could get electricity costs down on a per unit thermal basis, close to what natural gas would be, you just run a big electric arc or even a resistive heater. So those are all feasible with low cost electricity.
But then you lose the benefits of energy return, and you're probably very close to negative energy return on investment when you're starting to do that with renewables. Is there a nuclear solution that competes?
We've talked about it. District heating, though, is a challenge because you can't get that heat very far. Electricity is easy to transport, but the balancing the grids, at least in the US, we have more than enough generation capacity. Its problem is where and when do we have that capacity? So if you add a economic storage solution to the grid, the methanol electrolysis versus fuel cell is a reversible process, right? You can go both ways. So
yes, you can.
That would be my argument is this, once you solve the storage problem, you've got it licked.
That's no small hurdle.
So just to summarize, the challenge is what we've been seeing is that this 85% of energy coming from fossil fuels. What do? You have to take bites at it somewhere, and the solutions of batteries is the only answer, or hydrogen is the only answer, are not comprehending the bigger picture. And we're both saying, hey, look, the economics and the usefulness and the flexibility of doing chemical energy storage makes a heck of a lot more sense.
Yeah. That's what nature did. Learn from nature,
I do see Tim Rickman. Yeah. Go ahead, Tim.
Yes. Okay. Thanks. This was something that John Bucknell said early on in his talk, kind of in passing, that making hydrogen or presumably methanol from intermittent sources doesn't work very well. And this is going to be something that we'll all have to argue about a great deal, because of course the pro-renewables people will say, oh no, it doesn't matter that our renewables are intermittent, we can just make hydrogen. with the surplus. So I'm really keen to know just how difficult, if it can be quantified in any way, just how difficult is it to make, is it possible? Is it?
Let me give you two answers to that. Certainly, the challenge in most new manufacturing facilities is the amortization, right? You have to pay for the capital that you use to put it up. So if your capital cost is a large fraction of your total, then if it doesn't run all the time, your end outcoming products would be more expensive. Number two is that thermal inertia thing I've told you about. If you're using thermal or processes that are moving fluids, stopping and starting that doesn't work well. It's very, very hard to do a chemical or industrial process that stops and starts and stops and starts. It's just a general rule of thumb from manufacturing and industrial processes that are trying to maximize economics to make it the best, lowest cost, to make it feasible. Otherwise, you end up with a solution that's more expensive than the hydrocarbon solutions you're already dealing with. And that's really the challenge, is that if we end up with a solution that's more expensive than what we're doing today, the economic impacts to the rest of the economy are really bad.
Yeah, I mean, both myself, and I think it was Jessica Lovering and her lot, modeled this business of the more intermittent your energy is, or the intermittent part, the most intermittent part of your intermittent energy is so expensive in terms of the plant that has to stand idle all year waiting for it, that it's actually inevitable that you'll finish up discarding some of it. And you can argue over how much you'll discard, but you'll certainly discard some of it in order not to have the plant to deal with it. And that not only puts the price up, it also puts up the carbon footprint of the rest of it, because some of the total is being discarded. Yeah. Okay. Any sources, any quantitative sources that you can send us to that will give us ammunition to argue with the?
People have looked at it. I think the most important thing is a good electricity grid is important. Okay, if you really want to manage this electricity and the costs, you need to have a good, stable grid where the electricity, surplus could be managed. Yeah. Yeah.
I mean, of course, the problem in future is going to be that we're moving to a situation where, I mean, even nuclear, although it can load follow, for example, we're going from a situation now where we create fuel in the quantities we create energy in the quantities that the load demands. We'll be going to a situation where essentially the creation of energy is at best constant to go with a varying demand. And the more we let intermittents climb into the scene, it will be not only a varying demand but a varying supply as well. So it's not so much the production of energy that's an issue in the future. It's the what you might call intermittency, the mismatch between the supply and demand. So that's one of the reasons I try and fight off the intermittent people.
Yeah, I mean, the intermittency is a challenge to the grid no matter what you do. You either get energy storage or low cost base load, and the choices are limited. And I hate to put a plug in, but if you guys chase down my company, that's something we're trying to solve. So we'll talk about that maybe in a future forum. So yeah, it's a big problem.
Okay, only a couple minutes left. Gabe, do you want to get the last word in?
Yeah, I'm wondering if that intermittency problem could be solved by just using the wind and solar infrastructure to make methanol, and that's it. Keep it off the grid.
Yeah, that's what. See, one of the suggestion is, you can breweries, for example, where they make alcohol, the CO2 that comes out of the breweries are very clean. So in many reservations, you can generate a lot of Indian reservations. They are making already alcohol. So we can capture the CO2 with wind or solar. We can make methanol. In fact, that is one of the ideas we were talking to people about. So it's a distributive generation, maybe the way to go. And distributive way of making methanol.
Excellent.
Good question. Yeah.
Well, I think we've reached the end of our time slot, so I'd like to thank our presenters again for great presentations. That was very interesting and helpful, and sparked some great discussions. Really, really appreciate you guys coming and letting us know all of your work. And how that's going to get us out of this hole that we've dug for climate.
Very good. Thank you.
And thank you, everyone else, for coming to listen of the Eco-Modernist Society of North America. And hopefully you'll rejoin us for our future symposia. Thank you.
Okay,
very good, everyone. I'm going to cut the broadcast. So thank you all to everyone watching at Your Environment Seattle on twitch.tv, Your Environment Seattle on YouTube, and on Facebook. Thank you all.